First of all, hello everyone in the office and in the Zoom. So today we're gonna discuss a topic that's kinda exotic at first, because it's something that combines data engineering, data science, and software engineering as well. But I hope it's not gonna be boring and that you'll have a good time. So the topic is designing and implementing sparse matrix reduction in Apache Spark. So in general, Spark is a general purpose distributed computing engine. And it can be used not only for ETLs that we do daily as data engineers, but also, for example, for machine learning, implementing some linear algebra kind of stuff. So let's begin with who actually I am. So I'm a junior big data engineer here at Grid Dynamics. I graduated from Jagiellonian University with bachelor's in computer mathematics. And I'm obviously interested in data engineering because this is my role. But also the more relevant topics today are topological data analysis and machine learning, especially deep learning. So what's the agenda? What we're going to talk about? So I'll begin with the motivation. So where actually this matrix thing come from? So this is not an example out of nowhere. It's actually coming from real world tool. Then I'll present the pseudocode for sparse binary matrix reduction, and we'll start with single machine version. And then I'll show you how this single machine version can be actually improved or extended to work in a distributed scenario. Then we'll do a break, and then we'll start engineering. So I'll show you how this theoretical distributed computing algorithm can be implemented in Apache Spark, and of course with Scala. Why Scala? Because we are going to do some low-level APIs. We're going to use some low-level APIs, which in PySpark would be too slow. So the motivation. So the motivation is persistent homology, which sounds like nothing that nothing familiar. But I'll show you what is it about. So, but to start with, we need to know that in mathematics there's like a sub-branch of mathematics called topology. And in general, topology deals with similarities of shapes. And also, even more, of these similarities of shapes. So for example, in the GIF example on the right, we see two shapes that are topologically equivalent. So as a topologist, you say that these two are actually the same. And topological data analysis is then an approach of analysis of point clouds, so just set of points, using techniques from the classical topology. And TDA, or topological data analysis, has two main branches, two main tools. One is persistent homology, and the other one, mapper. About mapper, we are not going to talk about today, but persistent homology, yes. So what do we see here? So immediately when we see something like that, our neural net in the brain says, yep, this is a point cloud sampled from a circle. But the question for persistent homology is to, in a way, reconstruct the original shape that the point cloud was sampled from. And we don't even care that much about the actual full shape, but we care about the number of holes in the original shape. About holes. There's a tool in classical algebraic topology called homology that does exactly that. So it counts number of holes and the voids. So this concept of hole generalizes into higher dimensions. So for example, the empty space within a ball is also a hole, and so on in higher dimensions. So for example, in these two examples, we have on the left a shape that has one hole. So this empty space that's enclosed by the loop. And on the right, we have a shape with two holes. And the number of holes is something that we really care about in this type of analysis. Okay, we had a full shape, but our problem is related to point clouds. So we do not have like a full shape by default. Like the point cloud doesn't have any kind of, interesting structure when it comes to topology. So we want to, as I said, in a way, reconstruct the shape. And how can we do that? So we can, for example, create a graph based on this point cloud. And by graph, I mean connecting each two vertices that are sufficiently close to each other. So, for example, in the example in the left, there's a point cloud. It looks like it was sampled from a circle, but we do not add any edges yet. In the example in the middle, we add only edges between those points that are really close to each other. And in the last example, we kind of increase the distance threshold. So we connect more points. And this way, we reach a shape that's topologically similar to a circle because it has one hole. But as you saw in these examples, the definition of sufficiently close is kind of problematic. Because first of all, too small threshold distance might not show holes of the original shape at all, as we had in the middle example. But if we allow too large threshold, it may show actually too much holes. So for example, we can imagine that we make this threshold infinity, and then we would have a full graph, so a click, which has many holes. And to solve that, persistent homology does two things. So first of all, it not only creates a graph, but also if 3 points are sufficiently close to each other, it creates a filled triangle with them as vertices. So in this way, it kind of fills a hole. So it removes one hole. And analogically, it proceeds with 4 points and so on. And the other thing that it does is that it can solve for every possible threshold value, which, when I first heard about it, I thought that it's impossible, or at least really inefficient computationally, but it is possible. So yeah, persistent homology. As an input, we get a set of points, so a point cloud, and as what we get as an output. So in general, this is often that we get a persistence diagram, which is a set of pairs where each pair represents a birth and death of a hole, meaning that a hole was created at distance threshold birth and was filled at threshold depth. It might be the case that the depth is actually infinity, so the hole is never filled. In this example, we see an example of a persistent diagram, which actually is the output of persistent diagram of a point cloud that was sampled from a circle. So we expect to have one hole. And indeed, this yellow dot represent that hole that we are looking for. And we see that its birth is around 1, threshold 1, and depth around threshold 5, which means that it's kind of persistent across increasing the threshold. So it's not a noise of the data for sure, but also we have some noise of the data. We see the noise of the data, but it's close to the diagonal. So we have some points, these yellow points close to diagonal, but they have almost the same birth and the depth threshold, so they immediately are filled. So these are kind of noise of the data. And about the blue dots, they actually represent the number of connected components of a shape, where one connected component is here, and it represents that one connected component was born at birth 0 and has never died, because this line represents infinity in this in the output of this library, which is scikit TDA. I don't know, everything's cool, but how does it work under the hood? So we get a set of points as an input, and the magic of topology and abstract algebra reduces the problem to a matrix reduction. However, I do not have time to, jump deeply into how it works, and we have to, unfortunately, go into the matrix reduction, because this is the topic of today's talk. Sparse binary matrix reduction. As I said, we'll begin with single machine version. So there are a lot of buzzwords in even in the title of the presentation. So let's begin with explaining the first one, which is binary. I mean, binary is pretty obvious in a way, because it means that all of the entries in the matrix are either zeros or ones. But the caveat here is that the rules of addition are not the same as in usual maths. So 0 plus 0 is 0, nothing unexpected. 0 plus 1 is 1, so again, nothing unexpected. But 1 plus 0 is again 1, so that's fine. But 1 plus 1 is not 2, which might be surprising, but it's not 2. 1 plus 1 is actually, in this sense, 0. So it's actually, this addition is actually the same as binary XOR, whatever the analogy you prefer. But yeah, just keep in mind that 1 plus 1 is 0. And what is sparse? So sparse in general is the opposite of dense. And what is dense? Dense means that we store everything. But the matrices that are arising from persistent homology have vast majority of entries equal to 0. So that's why it doesn't make sense to store the matrix as a dense one. So we can store the matrix internally as a list of columns where each column has this sparse representation. What do I mean by that? We represent each column as a list of indices of ones. So for example, in this example, we have a matrix that's translated into the sparse representation where first column has only 2, so element 2, which means that there's only one in the first column, and it is at index 2. And we see that it's clearly the case, index 0, index 1, index 2. For the second column, we this time have 2 entries in the list, so 0 and 3, which means that the second column has 2, 1 entries, The first one is at index 0 and the second one at index 3. And the last column actually is a 0 column. It does not contain any ones. That's why we represent it as an empty list. You know, to show you the pseudocode for the reduction, I need a helper definition, a pivot of a column. So given a binary column C, we define its pivot as maximum value among indices of ones in C. And if there are no ones, for convenience, we set the pivot to -1. So for example, I mean, in other words, it's the index of the one that's the most on the bottom for each column. So for example, in this matrix, we have for first column, there's only one, so there's nothing to choose from, right? So this one is at index 2. So a pivot is 2. Pivot of this column is 2. For the second column, we have 2 ones, so we have something to choose from. But the one that's more on the bottom is this one, and this one has index 3. So pivot of this column is 3. And for the last column, as it is a 0 column, it does not contain any ones. We set the pivot as -1. Okay, we are ready for the pseudocode first for today. But yeah, let me first say, what does it mean that a matrix is reduced? Actually, it means that no two columns in this matrix have the same pivot. At least if they are not 0 columns. If they are 0 columns, we do not care. But if they are non-zero columns, we do not want to have 2 columns with the same pivot. And to like change the matrix in a way that respects linear algebra and also changes the pivots, there's a pretty simple algorithm. But you know, the caveat here is that it works only for in a single machine. So we get a matrix as an input, and for current column in matrix, so we iterate over columns of the matrix, and it's important that we do that from left to right. And while there exists a column C, that's before, so to the left to the current column, that has the same pivot as current column, we just add this column to current column. And what then happens? As these two have the same pivot, so they have at the same index ones, I mean at the most bottom one. And as we remember, in the binary addition, 1 + 1 is 0. So those current columns pivot changes, and it actually decreases, always decreases. So we are guaranteed that this algorithm will leave at the end the matrix reduced. Yeah, let's go through an example. We'll try to reduce this matrix, and let's do iteration by iteration of the for loop. So for the first column, there's nothing to do because there's nothing to the left of that column, right? It's the first one, so it's already reduced. For the second one, there's one column to the left of it, but this yellow column, so the current column in the pseudocode, has pivot 0 because it has one at index 0. But the column that's to the left actually has pivot -1 because it's a 0 column. So pivots are not equal, so we are fine. And this column is also reduced without any interventions. For the third column, again, the same story, but this time we have 2 columns to the left of it. But both of them have different pivots. So this one has -1, this one has 0, as we said, but the pivot of current column is actually 1, because it has the one at the bottom with index 1. And the only actually interesting case is for the fourth column. So to begin with, in the fourth column, we observe that there's a column to the left of it that has the same pivot, which is the third column. And what this algorithm does, it adds this third column to fourth column, and the result is this column, right? Because we have 1 plus 1 is 0, and 1 plus 0 is 1. Yes. But again, remember that there was a while loop, so we need to check again. Maybe there exists a column with the same pivot as this one. And indeed, it does. The second column has the same pivot as the fourth one. So we need to perform the addition again. And we do that, and we are left with a column that contains only zeros, which is reduced. Because we do not care about 0 columns, because if we cared, then we would add 0 column to 0 column, and it would not change anything, and we would be stuck. So if a column is 0, we say that it's already reduced. And for the fifth column, we see that its pivot is 2. And to the left of it, there are no columns with pivot 2, so we are fine. This column is reduced. And we are at the end of the for loop, so we have a reduced matrix. Okay, time for first Q&A. If you have questions, either ones in the office or those that are on the Zoom, please raise your hand, and our moderator will check.
Hello. There are two questions. First of all, about binary matrices. Are there any algebra for basic operations for matrices for us that we can perform without the compression of these matrices? Like we had 2 sparse matrices, and we want to add them plus operation. And can we do this plus operation in reduced matrices or no? And second question about what kinds of types can we reduce like this, or just binary? That's all. Thank you.
Okay, so I'll begin with the second question. Like that, you can only reduce when it's binary, but persistent homology allows, I'll be mathematical here, any field. So it can be field of real numbers, it can be like, field of 3 elements, so like 0, 1, and 2, with some, with the rules of addition modulo 3. But then the algorithm a little bit changes. This one with binary elements is the most simplified one, but also one that is sufficient in most cases. Also, for non-field elements, they can be actually some kind of rings, but this is some. Then the reduction is a lot different than this one that I presented. And about the first question, the question was, correct me if I'm wrong, if with this sparse representation of the matrix, we can do like the basic matrix operation like plus and minus, I don't know, the dot product of matrices. And the answer is yes, if you implement it. It is possible, but for the persistent homology, there's no need for that, because you always have a one matrix, and you operate on this one matrix. You do reduction on this one matrix. But I believe, yeah, for sure there are, for example, the linear algebra library that SparkML uses. It's Breeze, I believe. I think I checked, and for sure it has sparse matrix, class, and for sure it has basic and not that basic, linear algebra operators like plus and so on. Does it answer your question? Okay. Any more questions? Okay, I believe not. Okay, let's continue. Okay. So now be prepared, because this is the hardest part actually of this talk. So we are going to make this simple algorithm distributed. The matrix might be too big to fit in a single machine, but the algorithm that I presented is pretty limited. I mean, when we are reducing a column, we first of all need access to have to all preceding columns, right? So this makes it like a poor candidate for distributed algorithm. And the second thing is that this algorithm has left to right for loop, which means that it depends on preceding columns to be already reduced. Okay, what to do with that? So the idea is to split the matrix into blocks. Like here in the example, we have several blocks. But what to do then with those blocks? So what not to do? Do not try to treat each block as it was a matrix, and do not try to reduce them then in parallel. It will not work. Why? So first of all, a single column is not splittable. So linear algebra doesn't allow us to split the column and just operate on the part of the column. So we need to add full columns, the entire columns. And as we have to add entire columns, if we would then reduce blocks that are vertical, we might mutate those columns in two different nodes. So we reach the inconsistency and undeterministic behavior. And at the end, we will not get a reduced matrix, or at least it will not be correctly reduced. So what to do? So first of all, to helper definitions, trust me, these are going to be, I believe, two last ones. So we say that a block is reduced if a submatrix that's ending at top right of this block is reduced. So for example, this blue block is not reduced. The submatrix that we are talking about is this green one. And obviously, we see that in this green submatrix, there are two columns with the same pivot. So this one and this one. They have the same pivot. So this block is not reduced. About the second example, the red block is actually reduced. The submatrix we're talking about is the green one. And we see that there are mostly zeros, 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 and two non-zero columns, but they have different pivot. So we're fine. And we say that a block is reducible if block one below it and block one to the left of it are reduced. So as an example, so first of all, we observe that every green block is reduced. Why? Because if we check matrices that end at top right of each block, of each green block, these submatrices contain only zeros. So they are reduced. But as green blocks are reduced, all blue blocks are reducible, because for each blue block, the one to the left of it and the one below it are green and reduced. And that's promising. And now the critical observation is that all reducible blocks can be reduced in parallel. And once the top right block is reduced, we have a reduced matrix, because the top right one, the submatrix ending at top right of top right block, is actually the entire matrix. So how to reduce a block now? So we are given a reducible block and we want to make it reduced. And we actually can use almost the same algorithm as in the single machine version of matrix reduction. The only difference is that we only reduce columns that are both within blocks column range. So the range that spans the block. No, I'll show you an example in the next slide. It will be easier to show like that. And not only they have they are within blocks column range, but also their pivots are within blocks row range. Again, I'll show you what it actually means in the next slide. But in this way, to reduce a block, we only need to have access to columns that are from blocks column range with pivots within blocks row range, and columns that are preceding the block, so to the left of the block, that have pivots within blocks row range. About these ranges, let's go to ranges. By column range, I mean columns within blocks column range are those. This. And blocks row range is actually this range, right? So as I said, what if we want to, this, first of all, this block is reducible, trust me or not, but it is. So we can make it reduced with this algorithm. And which columns do we need to do that? So first of all, I said that we need columns within blocks column range, so those, but that also have pivot within blocks row range. And there's only one column, this one, with the yellow dot above. The rest have pivot that's outside of the range of this blocks row range. And also I said that we need to have columns to the left of the block that have pivot within blocks row range, so within this range. And there are three, which have dots above. This one, and this one. And these are all that we actually need to reduce this block, which again sounds promising for the distributed version. So how do we now split the work into stages? And by stage, I mean a logical stage, and also this will be the shuffle stage in Spark. So one shuffle stage will be, I forgot to mention that matrices arising from persistent homology are all upper triangular, which means that below the main diagonal, there are always zeros, which means that all of the blocks below the main diagonal are reduced. So we do not have to do anything with them. So we just have to start with blocks that are on the main diagonal. So in this example, they are colored green. And as all of them are reducible, by the observation that was made, they all can be reduced in parallel. And what's more interesting, even more interesting, not only in parallel, but also the set of columns that they need for the reduction is distinct for each block. So we can actually split the work between nodes in the cluster, where each node, in a way, reduces one block, and there will be no, duplication of columns that will need to be in, for example, two nodes. It's always guaranteed that one column needs to be only on one node in this way. So we divide into stages. Stage one would be reduce all green blocks. And once they are reduced, we can go to the next stage. And next stage is these diagonal blocks, but on the one level to the right and top, right? So blue ones. They are reducible, so we can reduce all of them in parallel and in different nodes. And once they are reduced, we can go to yellow ones, and so on and so on. At the end, we would get reduced matrix. Okay, again, pseudocode. How to reduce a block? As I said, it's pretty similar to algorithm to the single machine version. So we get a block as an input. And by block, I mean all of the columns that are needed to reduce that block. And we again do a for loop from left to right for current column in block columns within blocks column range. And again, while there exists column C that's before current column, such that it has the same pivot as current column, and also that this pivot is within blocks row range. If it is the case, we add this column to current column. And we continue until there's no other column to the left of current column that has the same pivot. And the pivot is within blocks row range. So important notes here, I already mentioned that, but in the columns addition step, we add entire columns, not just the parts within the block. So the column is not splittable. We need the information about the entire column. And the second note is that column C does not necessarily need to be within blocks column range. I already showed that there can be columns that are to the left of the block that we need, and we'll use them then. Now, last pseudocode before we do engineering in Spark. How to now reduce the matrix. So we have reduce block function that I showed previously. And now as an input, we have the entire matrix. So we begin with splitting the matrix into blocks that in general should be square ones with equal size. And then for each diagonal blocks level in blocks, so we start from main diagonal blocks. So in the example I showed you, the green ones, and we are heading towards top right. So after green ones, we do blue ones, right? So we begin in each iteration. We first distribute each block from diagonal blocks level to a different node. And in parallel, we run reduce block for each block in this diagonal blocks level. Then we wait for those reductions to complete, and we go to the next diagonal blocks level, and so on and so on. And at the end, we get reduced matrix. Okay, time for the second Q&A. And after this Q&A, we'll do 5 up to 10 minutes break. Okay, do you have any questions? Okay, seems that we do not. So yeah, let's do 10 minutes break, and we'll start the actual engineering in 10 minutes. Okay, let's get started again. So, uh, first of all, I hope that you can still hear me. And let's begin the engineering. Let's stop doing the mathematics and start doing engineering in Spark and Scala. So first of all, how can we represent sparse binary vector? So our column. Well, of course we'll use class, but we'll get in the constructor a list of indices of ones. But important thing is that this list must be sorted in descending order. Why? Because then the pivot of this vector of this column is just ahead of the list. For convenience, here we use Scala's option instead of just having it as a long. So in case the vector is a zero vector, so it does not contain any ones, we set the value of the pivot to none, otherwise to some head. But why is it important? Why is it important? It's important because in Scala, list is actually a single list, single linked list. So taking a head is a constant operation in terms of time complexity. And if the sorting would be in ascending order, we would have to get the last element which is O of n, so linear. But also we needed the addition of columns of vectors. How to do that? So, no, I don't know what about you, but I pretty much like functional programming. This is why we might try to do that with the core concept of functional programming, so recursion. Yeah, let's try. So how would we approach this problem? We have some other vector, and we want to add it to this, right? This object. So first of all, we define this helper function that's going to be actually recursive, ox, which takes two lists of longs, which represent indices of ones of two vectors, A and B. In case you do not know Scala, this AB match will pattern match the pair AB. So in case both A and B are nil, we have nothing to do. We are adding, in a way, two zero vectors. As a result, we get zero vectors, so we return nil. In case A is not nil, but B is nil, we just return A, which is aliased as X's in this code. In the symmetric case, when B is not nil, but A is nil, we return B, aliased as Y's. And the interesting case is when both are not nil. So we decompose A into X cons rest X, which if you don't know Scala, it's like X is head, and rest X is the tail of A. Y, and B into Y, cons rest Y. So Y head and rest Y tail of B. And now we have three cases. So first case is when X is equal to Y. What does it actually mean? Well, it means that A and B, the initial vectors, have one at the same index, at index X, which is equal to Y. And it means that we are trying to add two ones. And as a result, as I said, in the binary addition, 1 plus 1 is 0. So we return ox of rest of X and the rest of Y. So we skip the X and Y at all, because they reduce to 0. Else, if x is greater than y, as we want to keep the descending order of the result, we have to put x first. So we do x cons and the recursive call ox of first of x and b. And else is the symmetric case when y is greater than x. Then we need to put y at the front. So y cons. So we add y to the front of the list, and the tail is recursive call ox of a and the rest of y. As a result of the addition, we just return new sparse binary vector with the results of the ox helper addition. And it looks good, it works, it's pretty clean, but there's a major problem. It is not tail recursive, and as it is not tail recursive, it will eventually and pretty soon result in stack overflow. And as we are in big data, we cannot just let it go. We just cannot, let the jobs fail for that reason. So in case you don't know, tail recursion is a recursion that where the recursive call is made as a last thing that's done in the function. So let's try to make it tail recursive. And it actually is not that different. We're gonna use pretty common pattern of accumulator. So first of all, we see that there's this tail rec annotation added, but of course this is not something that makes function tail recursive. It is only something that checks at the compile time whether the function that's annotated with tailrec is actually tail recursive or not. If it's not, the compilation will fail. But you have to trust me that it doesn't fail in this case. So what changes? We again have this helper function ox, but now it not only takes a and b, but it also takes an accumulator, which is initially empty, so nil. And we will accumulate the results here instead of after the recursive call ends. So again, we match on a and b, and again, when both a and b are empty or nil, we do return just the accumulator, what we have accumulated so far. In case a is not nil, but b is nil, we decompose a into x and the tail rest x, and we do the recursive call ox, and we add to the accumulator x at the beginning and the accumulator, and as a new a we put rest x, and as b was nil, it's still nil, so still nil. This case is symmetric. Instead b is not nil, so we add y at the beginning of the accumulator. And the interesting case again, when both are not nil, and again, if x is the same as y, we have 1 plus 1 equals 0. And we can skip x and y, so we just do the recursive call on ox of accumulator and the tails of a and b. Else, if x is greater than y, then again, we add x at the beginning of the accumulator, and we do the recursive call. And the last case, symmetric, but y is greater than x. Right. But there's a caveat. Actually, this implementation of the ox will return the result in ascending order. You can imagine how it works, but I'm not going to prove that this is the case, but this is the case. So we have to reverse the list before we create a new sparse binary vector now. But as reverse is a linear operation as well, this addition is linear, we do not gain any, at least asymptotic complexity here. There can be done one more small improvement, but it's really small. So we can minimize the number of objects created by creating a singleton of empty, representing empty vector. And we do that, we are creating in Scala object is a singleton. So we do create an object empty that extends sparse binary vector of nil. And we can also override the plus, because anything plus empty is just this other vector, right? Yeah. And also in the class sparse binary vector, we can do some optimizations, small. So if we are adding empty vector to this, result is this, right? The same object. And as this object has only immutable fields, so immutable list indices of ones, we can safely do that. So this is also a common pattern in data structures in functional programming, that we reuse objects, immutable objects. And else, so when other is not empty, we calculate the result of the helper call. And if the result, so if we add to the same vectors, we'll get an empty vector as a result. So instead of creating a new sparse binary vector of nil, we just return the singleton, the empty. And else is the same as before. Okay, now Spark. How to represent the matrix in Spark? Well, matrix arising from persistent homology is square, that's first thing, and it has sparse column, as I said. So it kind of makes sense to represent it as the matrix as a data set of sparse binary vectors. However, it will not work with this implementation, because we will be doing some low-level APIs that are not available in a data set. So instead, we, unfortunately, with this implementation, of course, have to use RDDs of sparse binary vectors. So how to translate what was in the pseudocode of the distributed algorithm to the Spark implementation? So first of all, in pseudocode, nodes are going to be RDD partitions. So in pseudocode nodes, here we will be talking about partitions. In pseudocode, distribute each block to a different node is going to be repartition of the RDD based on a custom partitioner. Reducing one diagonal blocks level is, in Spark language, map partitions on an RDD. And block reduction in pseudocode is going to be just a normal Scala function that as an input gets iterator of sparse binary vector. And left to right processing inside the block in the pseudocode is going to be achieved by a for loop over sorted partitions. So actually, we are not going to use repartition, but repartition and sort within partitions. The difference with using repartition and sort within partitions against repartition and then separately sort is that here sorting happens at shuffle stage, which is much faster. Okay, some more technical details. So actually, to use a custom partitioner in Spark, we need an RDD of key value pairs. So we are actually gonna represent the matrix as an RDD of key sparse binary vector pairs. And the key is going to be just a simple case class that contains information about the index in the matrix of a column and its pivot. To keep information about pivots of columns, to the left of currently processed column, we'll be using a mutable hash map where keys are, of course, pivots, and values are columns. So the custom partitioner that we're gonna use is called pivot partitioner, and it takes into account only pivots of columns. So a custom partitioner in general in Spark needs to override one method, so get partition, and based on a key, on some kind of key, it assigns the value with that key to some partition, to some number, like index of partition, right? So if, for example, the size of a partition is n, so we set it to n, then at each stage, first partition is going to contain columns with pivot in range 0 up to n excluding. Second partition from n to 2n, and so on. And to make repartition and sort within partitions work, we need ordering of keys. And we can just have an implicit value key ordering that's ordering by index in matrix of a column. Okay. So now translating the reduce block from pseudocode to Scala. So we have reduce block. It takes as input partition. As I said, it's just an iterator of key sparse binary vector pairs. It also takes block column range, which is a pair of longs, and block row range, which is also a pair of longs. And of course, we must return some kind of iterator. And as we are not changing the structure, we will be returning iterator of key sparse binary vectors pairs again. But yeah, there will be some columns at each stage that are useless in this stage with this partitioning. So first of all, we split the partition iterator into 3. And this span, actually this Scala method span, what it does, it splits the iterator into 2, where first one contains all entries that satisfy this predicate. So in this case, we split partition into columns already reduced and those unreduced. And how do we know if a column was already reduced? We just check if it's to the left of the block. So we check whether index in column is less than block column range the left side. But then we need to split again unreduced. We again do span. And in this case, the predicate is whether the index in matrix is less than or equal to block column range, the right side, right? So in this way, in unreduced to process, we have all columns from the column block range. And in to reduce later, we have all columns that are to the right of the block. And we are not going to touch them at all during this this stage. As I said, we're going to use mutable hash map. Mutable because we're going to do a lot of mutations, and it's going to be more efficient. Yeah, what happens here is that we set the reduced as a hash map, and we initially put there all already reduced columns. But again, as I said, the key of this hash map is a pivot, and the value is a column. And we'll also need columns that will be processed, but they will be after the reduction still unreduced. What I mean by that is that a column can be reduced at this stage as much as possible, but at some point when we add other column to it, its pivot might go too low. I mean, outside of the blocks row range, and we'll keep them here in this list. Initially nil. And this is the for loop, the same as in pseudocode. So we iterate over unreduced to process columns. We initially set variable, so we're gonna change it of current column to the column that's from the iteration. And while this column is not zero column, so its pivot is not empty, and the hash map, reduced hash map, contains current column's pivot, we add that column to current column, right? So we said current column is current column plus reduced of current column pivot. And this is actually the meat of the algorithm. And at this stage, we already have reduced as much as possible, at least, current column. So for convenience, we first get its pivot. And as it's an option, we do get or else. So if it's none, we set it to -1. And if pivot is within blocks row range after the reduction, we put it into the hash map. If current column is not empty, else if current column is not empty, we add it to process but unreduced. Because in this case, we know that the pivot is outside of the blocks row range. Yeah, so we add it to process but unreduced. And in case it is 0, we throw it away because it's useless. 0 columns are totally useless for this reduction because they can be later restored. As we know, the initial full size of the matrix and non-zero columns. This way we can restore easily our 0 columns. And at the end, we just return iterators of reduced, hash map converted to iterator, process but unreduced converted to iterator, and to reduce later. There's also a slightly improved version, but although it's not super optimization, but at least if you know what transformation to transformation, iterator to iterator transformation is in Spark, in core Spark. This is something that tries at least to make it partial. So partially iterator to iterator transformation. Of course, it cannot be done fully because there's a hash map mutable that we need to then unpack, but at least partially. So instead of for loop, we do a flat map, and we put the results of the flat map in process but unreduced. Almost nothing changes except that we need to, from the flat map lambda function, we need to return some kind of iterator. And in case we add eventually the current column to reduced, we return nothing because the result is in process but unreduced. If a current column is not empty, we add a single, like iterator single, so a single value as an iterator. And else the column is 0, so we do return iterator empty. And in this way, we are returning 2 iterators, not lists. But keep in mind that then the hash map must be concatenated as the last one. Because if not, the iterator would not, because iterator is lazy and it would not go through this code before, and the reduced hash map would only contain the already reduced columns that are put here. The custom partitioner, as I said, a role of custom partitioners is to assign partition index given a key. I'm not going to tell you what this exactly does, these calculations, because I already forgot, but I know intuition. Intuition is the same as I showed you. So if a pivot is within range 0 to n, it puts it in the first partition, and so on and so on. but there are some like math floors, blah, 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 nothing important. Okay, last part. Reduce boundary matrix. Where is this boundary come from? It actually, the matrices arising from persistent homology are called boundary matrices. So this is why, but this is just the same matrix that we were talking about. So we get, this is the reduced matrix from pseudocode translated to Spark. So this time we get as an input boundary matrix RDD of key sparse binary vector pairs and the desired number of partitions that we want to work on. So first of all, as you've seen or not, the pivot partitioner needs the number of column of the initial matrix, which is just a simple count on RDD. We then create a partitioner with the number of partitions from the input of the function and the number of columns calculated. Then we need this key ordering, already told you about it. And now we're going to have an iterative algorithm. So we create a variable called reduced matrix, which is initially just the boundary matrix we filtered out 0 columns. As I said, they are useless in the reduction in general. What we then do, we do repartition and sort within partitions based on this custom partitioner, pivot partitioner, which will move all of the columns that are needed to a correct node, I mean partition. And we can think about this step as in the pseudocode there was something like split the matrix into blocks. So here we calculate the block range length. Whatever the calculation is, doesn't matter that much, but it keeps all blocks the same size. So that there are that many, let's say, horizontal, at the same level, horizontal blocks as a number of partitions. And this is why we can do a for loop starting from 0 and until number of partitions. So this does not look like, you know, in the pseudocode we had 4 diagonal blocks level in blocks, but this actually is the same, more or less. I mean, at least the number of iterations is the same. Trust me or not, it is. And the actual meat of this function is that we change. RDDs are immutable, but we set the next stage. I mean, the next RDD. Set it to reduced matrix, and it is the current reduced matrix with partitions mapped. So we do map partitions with index. And what's inside the lambda of map partitions with index is only calculating the column range, row range, and calling reduce block. Column range is calculated somehow, row range also somehow, doesn't make, isn't super important. Some numbers, blah, blah, blah. But what's important is that then after we reduce each block, at this stage, we must repartition it again. Repartition and sort within partitions, actually, based on the same partitioner. Because map partitions with index, with this reduced block, will change pivots of columns, right? So we need to do repartitioning. And we keep going. And at the end, we get a reduced matrix. Yeah, this is how the DAG computations work. I mean, look like. There will be the same number of stages as we put the number of partitions, and each stage is really simple. So shuffle read, and then map partitions with index. So pretty small stages. And we control the number of iterations by changing the number of partitions, desired number of partitions. Okay, last Q&A. Any questions?
The ratio between time, volume, and the shuffling of the data.
Shuffling. I mean, there's a big like overhead of the garbage collector. It's cause oh, I hope you can hear me. So the question was, I'm not sure if you heard that. What's the ratio in the in the execution time for the shuffle, right? What's the ratio of shuffle volume? What do you mean by volume?
What I mean is, based on the size of the matrix and shuffle, I mean, how much is affected, the shuffling and the execution time based on the size of the matrix.
Yeah, as you probably know, I mean, for sure know, as RDDs are like the elements of RDDs are serialized by the Java serializer, not using some, as data set uses these encoders that are much more efficient. Here, if we somehow make the matrix too large with too little amount of nodes, like memory, then there will be a really big overhead of garbage collection. The shuffle itself, of course, this algorithm is shuffle based. I mean, it's not doing anything except shuffles, more or less. The reduce block is pretty fast. So it's majorly shuffle plus garbage collection. Does it answer your question? Okay.
Just curiosity. What can you list the specific limitations of dataset approach that you cover with RDD?
Yeah. So datasets do not have an option to be repartitioned by a custom partitioner, and this eliminates them at all from this implementation, right? Also, sparse binary vectors is a class that has some methods. It's not, and it has a list. I know that now in Spark, new Spark list have encoder, like the default encoder, but it's still not so obvious to encode a full class. Yeah, to defend myself, SparkML, like SparkML, the new SparkML theoretically uses data frames, right? So data sets as an input. But if you take a look in the code of the most of the machine learning models, the first thing that they do is that they convert this data set into RDD. And they start working from there.
Okay, last question. In which kind of real example you would use this approach?
You mean in the real world for this actual algorithm or in persistent homology in general? I would say, like, first of all, persistent homology is used, for example, in graph neural networks. There's a type of graph neural network called topological graph neural network. And it is, I know, I have read the paper like 1 year ago, but it was state of the art as of last year in protein classification. I mean, it calculates persistent homology. It's a little bit different. A little bit different assignment of when, whole, dice, and so on, but it's persistent homology. But if you are asking about this implementation, so the big data one, right? The answer is, I hope I would know. I was only implementing this algorithm. I don't know how it can be. So, I mean, of course, when you have, in general, yeah, let's go like that. In general, when you have even small point cloud, the matrix arising from this from persistent homology is huge. I think almost exponential. So even small point clouds, if we do not stop creating the matrix at some point, this is how it's done right now. They just artificially stop creating the matrix at some point because it will it would be, they would be unable to reduce it later, right? So this is one case, but my main idea when I was working on it like 1 year ago was that to make the flow, the entire flow, so starting from point cloud with Spark, create this boundary matrix, which is not obvious as well, and then reduce. But this is still work to be done.
So it was really cool, really interesting. And just to add something to your question, is something similar that you can use for the reduction of images. It's
Something
process.
similar, right?
Yeah.
Full algorithm?
Yeah, no, I mean, the reduction of image itself can be made with this approach.
You mean like a library or something like that?
Yeah, not as a library, but as approach did you never try to apply this kind of reduction to, high dimensional images to have good reduction?
No. And this was only used in this scenario of persistent homology. At least I used it like that. I mean, this is actually a good question, because this is like pretty, I would say, standard algorithm in linear algebra, because it's a variant of Gaussian reduction, but as the entries are binary, it's simpler. So yeah, maybe it can be used somewhere, but I haven't, thought about it.
This was not my question. The question was in the second optimization you presented. I don't remember. I mean, I need to digest all the code yet, but there was a one point. Yeah, this one. Yeah, this one was with the flat map, and this one versus the first one. Did you check optimization both from time execution and memory usage?
1% at most.
Okay. Thank you.
Okay, I think we do not have any more questions. So, from my side, thank you to everyone in the office and in the Zoom. I had fun talking to you. I hope you had fun listening to it, even though it was mostly mathematics that's kind of boring. But yeah, maybe in the future you'll see a full open source library for persistent homology. That's for Spark, and very likely it will be me that created it.